In chapter 8, we are going to learn about momentum and impulse. We are going to deal with collision, one or two bodies colliding together in elastic or inelastic way. And you're going to learn also about the physics of car crashes. Many examples will be analyzed when we do problem. Let me deliver a little bit of a theory. Impulse and momentum are really the key element for this chapter. What is momentum? It's also in simple word called a quantity of motion. Now, momentum, we are going to call it P. The quantity will be your mass multiplied your motion, which is quantified with your velocity. Momentum P, velocity are vectors because they have a direction and a magnitude. So how do we measure momentum P or quantity of motion? It's very simple. The mass is in kilo and the V is in meter over second. Impulse is actually defined by J in physics. And it applies when a force acts over a very short interval of time. J, the impulse, is also a vector. Think about that you have a bat, right? Here's your hand. And this is an object that is moving toward the bat, and you have to return it as fast as you can. So this delta T has to be very short, and the force that you have to give to the object with your arm has to be also very strong. So how do you measure impulse? The force is in Newton and the time is in second. Remember, they are both vectors. So in case you are going to find a momentum or an impulse on the x-axis that has an angle, let's say this ball moving with a certain angle like that, and this is, for instance, the momentum P, don't forget, so the velocity V will be like that also, wherever goes V goes P. In that case, you will have to do the component, right? So this will be the velocity x component, and this one will be the velocity y component. Now, I want you to see what's happened to the kinetic energy of a system, considering the momentum defined as mv. Kinetic energy was 1/2 mv square, v your velocity. Now I could derive v out of the momentum, right? So out of this equation I derive v. And I'm going to plug this quantity straight into kinetic energy, which will be 1/2 the mass momentum mass square. When you do the math, you will obtain that the kinetic energy is also defined very, very simple as momentum square divided twice the mass. So we can also rewrite the kinetic energy as a function of momentum P, this quantity of motion. As for the impulse, I want you to see very interesting things, very important things. I want to draw this impulse, right, is a function f, force function of time. It will be very much an arrow. The narrow is your interval of time, the more force you will be able to impart to this object. As you can see, impulse depends on your force and this interval of time. I'm going to actually spell it out, so it's a force, and this will be time final minus initial, where F stands for final and I for initial. So as you can see, it's a very handy equation which we can use many, many times. What's happened? If I rewrite the impulse as a function of the momentum, well, you recall Newton's law, F equal ma, and an acceleration is a change of velocity over time. So this force will be really mv over t, but I'm going to do a delta v over a delta t. I'm not changing nothing, I'm just substituting this one in Newton. So you see that right here at the denominator is m multiplied delta v, which is indeed your momentum. So your momentum now is m delta v. Why m delta v? Because I'm considering a case where the mass is multiplied by the final velocity minus the initial velocity of this object. If I do that, I can also obtain other information, because I'm gonna also take the time and I'm gonna multiply over there. So I'm gonna have force multiplied delta t equal m delta v. I already know that this one is the momentum p. But what is F multiplied delta t? F multiplied delta t is nothing else than your impulse j. So as you can see, we found out delta p, that your impulse is equal to the change in momentum. I'm going to say it again. Your impulse is equal to your change of momentum. I'm going to spell it out. The momentum is force multiplied delta t equal change of momentum. What does it mean? mv final minus mv initial. Or if you prefer, absolutely not a problem, delta t equal mass v final minus v initial. Now all these considerations are equivalent and they fall under the very famous theorem. This is the impulse momentum theorem. Very important, we are going to use it a lot of time. Impulse momentum theorem. All right, so we already have analyzed impulse momentum theorem. We analyzed what is the impulse with the unit. We analyzed what is the momentum, and we did a lot of consideration on the kinetic energy and the impulse also. And as you can see, again, the change in momentum gives you the impulse. The last information I want to give you is that when we are in an isolated system, what does it mean, isolated system? It means on this system there are no external forces. So no external forces that are acting. What does it mean? It means that your momentum P is conserved. So the initial momentum will be equal to the final momentum. This is a conservation of the momentum. Again, P initial equal momentum final. All right, let's move on. Because right now we have enough theory, so I want you to pause the video and do in chapter 8, do this first 4 problem. Astronaut rescue, analysis of collision, just to create the base. Very simple problem in preparation for more complex problem we are going to do together. Welcome finally to collision, elastic and inelastic. So we're going to do 2 types of collision. What's the difference? Very simple, stay with me, very simple. To begin with, we are going to consider, collision is between the 2 bodies or more than 1 body, right? 2 bodies, 2 or plus bodies colliding. So when the forces between bodies are conservative, oh, you say, what does it mean? Conservative means nothing else, I'm going to put it in parentheses, that there is no mechanical energy being lost, no mechanical energy loss. What does it mean in simple words? That your kinetic energy initial is exactly equal to your kinetic energy final. So conservative, nothing is lost in this mechanical energy. In this case, welcome, you are in elastic collision. Now you know that when the forces between bodies are not conservative, what does it mean? That there is a loss of mechanical energy. So what does it mean? It means that your final kinetic energy, if there is a loss, there is something that is being dissipated, so this kinetic energy final is less than your kinetic initial. In this case, you are in inelastic collision, right? Simple. 1 and 2. All right, let's analyze them in terms of math, so you are in great shape. The first one I'm gonna do is inelastic. This is a non-conservative. What does it mean? Final kinetic energy less than the initial kinetic energy. So let's imagine a body, I'm gonna call it A, which has a velocity 1 before collision. I'm gonna consider a body B, which has a velocity B, 1 because it's a before collision. Let's imagine that these 2 objects are moving toward each other. What's happened? They will collide. In elastic collision, these objects, they don't bounce back, but since it's inelastic, they collide and they become 1. So now there is the collision, and A melt into B. So now there is a new body. This new body will have the mass of A plus mass of B, what we call the combined mass. And this new object in elastic collision, they glue together, will be moving, let's say, to the right, for example, with a velocity 2 being 2 after collision, right? V of 2 is after the collision. So after the collision, the condition is that the velocity of object A after the collision will be equal to the velocity of object B after the collision, and is gonna be equal to this V of 2, right? Velocity after the collision. So for inelastic, what's happened to the momentum? Well, before the collision, the momentum, recall momentum is mv. The momentum of body A will be mass A, velocity of A1. Then I'm gonna add before the collision, mass of body B, velocity of B before the collision. This will be equal to after the collision combined mass, and the velocity after this collision is going to be called the V of 2. So this is a handy equation which I'm going to frame. This is a very important condition, and also this one is very important. Now we can solve this equation to compute the final velocity V of 2 after the collision as dependent of mass A, the combined mass, multiply VA1. Now I'm gonna frame it, but as you can see, you are gonna ask me what happened to VB1, to the velocity of object B before the collision. For simplicity, for this type of physics, we assume body B being at rest. So basically is 0. Just, to simplify, for simplicity reason, for the type of physics we are doing, lucky you. So we are almost done with inelastic. A couple of considerations about the kinetic energy K, which you remember, kinetic energy of body A of 1 before the collision will be 1/2 the mass velocity of body A before the collision square. What is the collision, the kinetic energy of these two bodies after? Because remember, 1 is before collision. So now I'm going to quantify with 2 the kinetic energy after collision. So K of 2, kinetic energy after the collision, will be dependent of 1/2, yes, the combined mass, multiplied a big parenthesis, and is a mass of A, divided the combined mass, I want you to put this in square, in parentheses, and put it square. Multiply velocity of A before the collision, also square, frame it. So this is your kinetic energy for inelastic collision to frame and keep on your summary. One little final detail is that I could do the ratio of K2, kinetic energy after the collision, over the one before the collision, and the physics again is so elegant, which will give the ratio of mass A over combined mass. All right, now I want you to stay with me, because I'm gonna move on to, I'm gonna leave this one on for a few more seconds. I'm gonna move on to the other type, the inelastic collision. So here in this elastic collision, the object bonds together and they go away. So this is a complex treatment. I will try to make it as easy as I can. So here is elastic collision. So again, you have two bodies that come together and they go, they bounce back. In this elastic collision, there is a conservation. Means the kinetic energy initial, it's equal to the kinetic energy final. So how do we treat this problem? First, if this happens, then also my momentum of object A must be equal to the momentum of object B. All right, let's spell this out. This is the condition. I've been repeating this many times. Conservation of energy means also the same momentum. All right, let's spell it out. Okay, kinetic energy initial, I'm going to put it here. What does it mean? It's going to be 1/2 mass of body A, velocity A, in stage 1 before the collision. Then I'm going to add the kinetic energy of body B, velocity of B, before the collision. And this has to be equal to the kinetic energy 2, final, right, after collision. So this is going to be 1/2 ma v of A after the collision plus 1/2 mass of body B, velocity of body B after the collision square. Frame it. This is the condition on kinetic energy for elastic collision. Boom, out. Let's spell out the momentum. What do you have? Again, before the collision, we'll have a momentum A, velocity A before the collision, plus the momentum of object B, with its velocity before the collision, 1, equal after. So it's going to be exactly the same, mass A, velocity of A after the collision, mass B, velocity of B after the collision, right? Again, 1 is before collision and 2 is after collision. Excellent. Frame this condition for momentum. Since also in this case we are going to do a simplification, such as the velocity of B before the collision is 0, so body B is at rest, not moving. Okay, object B is not moving for simplicity, right? For this type of physics, I'm going to conclude straight that VB after the collision will be given by velocity A before plus velocity A after the collision. Pretty amazing. Also, the velocity of object A after the collision will be proportional to mass of A, mass of B, and this is the combined mass. These are long computational, and this is proportional to the velocity A before the collision. And how about velocity of object B after the collision? Depends on twice the mass of A This is not a really combined mass and is a proportional of A velocity initial before the collision. You can remove that comma. I'm gonna make a simplification right there. Perfect. Okay. Let's move on, because now you have to pause this video, practice a very simple concept that is from example 5 to 14. And we are almost done with this chapter. Just, stay positive and think like a proton. In chapter 8, problem 5, we have an easy situation. So you have, to begin with, there is a speed which is a scalar and is the magnitude of velocity, speed, velocity being a vector. This speed was 45 meters per second. So the mass of this ball was 145 G, stand for gram. Remember, we don't want a gram, we want kilogram, so we will have to go to kilogram. We want to find in part A the magnitude of P, where P is the momentum. So you recall the momentum P, it's equal mv. Let me put it down here. P equal mv. Excellent. All right. We also want to find, you see, how many joule of kinetic energy. We want to find the joule, that's the unit, of kinetic energy in part A. So we need to really work on the knowledge we acquired during the theory. For the momentum, for the kinetic energy in general is m, depend on the mass and this speed of the particle, but we can also write down the kinetic energy, do you remember, as a momentum square divided twice the mass. So either way is gonna be fine. All right, so let's do part A. I'm gonna start with the momentum, which is mv. The mass, I have to go to kilo, so is 0.145 kilo. Let me plug it in. And the V, it's up here, already fine in meter over second. So if you do the math, immediately you obtain the value of 65, and the unit, as discussed in the theory, are kilogram meter over second. Frame it. Final answer. As for the joule of kinetic energy, K, is going to be 1/2 mv square. I'm going to just plug in straightforward my mass in kilo. V was 45. Don't forget to square it. So immediately you obtain 1.5 10 to the 2 joule. Frame it, because this is the joule of kinetic energy of this object, which is a ball. Oh, you maybe wonder, wait a second, I want to use the other one for kinetic energy. I want to compute kinetic energy as a function of the momentum. Can I do that? Yeah, absolutely. Let's do it. Well, the momentum was 65. Don't forget to square it. Twice the mass And if you do the algebra, will come out exactly the same as above. In part B, we want to find how fast would a 57-gram ball, well, I know that I like a kilo, would have to travel to have the same amount of kinetic energy and momentum. So how fast this object have to travel to have exactly the same kinetic energy and P momentum. All right, let's do that. If they have to have the same kinetic energy, I know that the value for K has to be fixed at 1.5. And that the kinetic energy is given as 1/2 mv squared. So how fast? What does it mean? It means I want to find V. All right, let's do that. 1.5 10 to the 2 joule equal 1/2. The mass was 57 gram right there, which I'm gonna write it as a kilo, 0.057 kilo. Okay, I'm gonna put it here, 0.057 kilo multiplied V square, which is what I wanna find. All right? So this is my unknown parameter, which I'm gonna solve it for, because you see V out of this equation can be computed as the square root of twice the kinetic energy divided the mass. So perhaps you want to also keep this equation together with K. So basically, again, I'm going to already solve it twice. And the mass. Final answer, this 57-gram ball will be traveling, which is much lighter than the one before, at 73 meters per second. So 57 gram, let's see, 57 gram travel at 73. And this one was 145, almost double, travel at 45 meters per second. All right, now we have to reason on the momentum P right there. So same as we did before. The momentum has to be fixed to the value of 65 kilometers per second. I know that the momentum is mv, and I want to find v. So v is p over m. The momentum is 65. The mass was 57 gram, but written in kilo. And if you do the math, the final answer will be 1.1 10 to the 2 meter per second. Frame it, and problem done. In problem 8.8, you have two figure skaters. One weight 65 Newton. Let's say this is a figure skater, and that's your hand skating. And this is, I'm gonna call it A as 65 Newton. There is also another skater right here, and they are against each other in this way. And I'm gonna call this one weight of B equal 725 Newton. They push off, you see, they push off against each other on a frictionless ice, so the friction italic is down to 0. So once they push against each other, they move separately, they move away. So this skater moves back because he's the heaviest skater, moves back at a velocity of 150 meters per second. We want to find how fast this person A is moving also. So in part A, that's what we want to find. How fast the lighter one will travel. Very important to remember is that we are in an isolated system, like 2 astronauts in space, 2 skaters. So we have a conservation of momentum that you remember means the initial momentum equal the final momentum. Let's spell it out. mv final equal mv initial. Frame it because this is a recall and you're going to use it over and over again. What do we know? The weight of A, 625. Weight of a person B, 725 Newton. You do remember that the weight is nothing else than mg, another recall, mass and the acceleration of gravity. Why do I do that? Because I want to derive the mass. You see, I need the mass. Mass is needed. So I can get the mass out of the weight. Let's do that, okay? So mass of A will be the weight of A divided G, and mass of B will be as above weight of B divided G. All right, let's plug in. And weight of B is a 725 Newton divided the same quantity. So this one is a 63.8 kilo and the other one is a 74 kilogram. So that's the mass, the number of atoms in the body of these 2 skaters. Now remember that these 2 skaters are initially at rest. In this here, the way I really draw it are at rest before they push on each other. So I know that if I place a y-axis pointing this way, being positive, definitely this is a positive V, but hold on one second, sorry for the interruption, but I'm not gonna stop the video because really this video are for you. I'm gonna put this video out there just in the hope to help you. They're not perfect by any means, so again I apologize for the interruption. So this is positive because it points in the same, but this, how fast is gonna be? Is gonna be positive or negative? Well, since this velocity will point opposite to the positive x-axis, I know it's gonna be negative. All right. So we already derived a lot of information. Now, a good practice when it comes down to momentum is really to break down the initial momentum and the final momentum in this way. I have a momentum A and momentum of body B. These are initial. And I'm going to compute it just initially, so that you know. Initially, body mass B, velocity of B initial. So this is a good practice, is a good methodology. But in our case, since these two skaters are at rest, the initial velocity is 0. So I know that this is equal 0 and also this one equal 0. I want you to reason also for the final, will be object A final, mass of A, final velocity of A, momentum of object B final, proportional to the mass of B, velocity of B final. Okay? Yes, I want to be elegant because I'm going to say that is on the x-axis, so I'm going to put a very tiny small x next to AFX. So you know that this means on x-axis. Quick recall. Why do I do that? Because I'm going to apply my condition now, that the momentum final equal initial, which is the conservation of the momentum. So basically what I have to do is take all the final momentum, this will apply, this all the final, add them together, equal the initial momentum. Let's do that. So P final, you will do PA final, momentum of object B final, equal momentum of object A initial, plus momentum of object B initial. If you want to be really elegant, you're going to tell me that we are all reasoning on the x-axis, but it's not necessarily once you put the x-axis visually visible for us to understand what you're doing. Well, you know that this quantity right here is 0 because the object is at rest. The two bodies are at rest. So I'm left with PA final plus momentum of object B final equals 0. I'm going to plug in what I found. MA, velocity of A final, plus MB, velocity of scatter B final equals 0. We want to find the velocity of A final. So basically, this object, how fast is going to be velocity of object A final? That's your big question mark, which, as you can see, I can derive it out of this equation. How? This is very simple. I'm going to do the algebra, because I'm doing a little bit more theory, as you can see. The momentum of B final through the equal become negative, and then I'm going to divide it by the mass of A. At this point, you just plug in all the numerical value. You have a mass of A, mass of B, you have a velocity of B final. So you plug everything in and you will obtain the final result of 1.74 meter per second. So my question to you is, what does it mean, this minus? Is scatter A moving to the right or to the left? Yes, indeed, is moving to the left. Just in case you may be a little bit confused, I'm going to show you mass of B is this one. Mass of A is this one. And the velocity of a B final is given up here. Okay, so that's what you plug in to obtain the final velocity is 1.7 meter per second, pointing to the left, exactly as my illustration shows. On a frictionless, so friction is equal to 0, you have a pack A with a mass of 250 kilo, 0.2 kilo, that is moving to the right, so it's moving right that, to the right, toward a pack B, let's put it here, this, and this one has a mass of 350 kilo. B is initially at rest, is not moving. There is a collision. Okay, so after the collision, pack A, so after the collision, the velocity of pack A is this one to the left. And the velocity of pack B is to the right. Okay? So imagine this is B, A is moving toward the B, and then they move back out. So we wanna find in part A the speed of pack A before the collision. That's my big question mark. So find velocity of A before collision. Okay, so we are doing part A. So so basically what we are seeing here is momentum. You remember the momentum, want the mass, and want how fast the object is moving. What else I know? That there is a conservation of the momentum. So the final momentum on the x-axis, it's equal to the initial momentum on the x-axis. So perhaps we can use this important condition to find V of A initially, I for initially. I'm going to spell it out for you, the conservation of momentum. So it says mass A, velocity of A initially, plus, there are two bodies, mass B, velocity B initially, equal, so this is all initial momentum, equal the final, so it's going to be mass, velocity of A final, plus m, this is mass of A, this is mass of A, mass of B, velocity of B final. So on this side of the equal, you have all final quantity, A final, B final, A initial, and B initial. Excellent. Now we need to add the sign, so this is a good methodology, because I know that the velocity A final, this one goes to the left, right? So means this is gonna be negative. So velocity of A, this is gonna be negative because it's gonna be to the left. The velocity of B final, it goes to the right, so this is a positive, and I know the value. And I also know that the initial velocity of B is 0 because is at rest. So this one, this should be not a plus. This is at 0, they multiply, typo. Let me clean it up, okay? They multiply right here. That was a typo, I just saw it. So basically all of this one goes away and we are left with this parameter to find. All right, now we discussed theory, we did the consideration, let's plug in our value. Mass of A, velocity of A initially is what I want to find, I don't know, equal. Mass of B, mass of A, multiply the final velocity of A, which was that the negative, I'm going to put it here, that the negative value of 0.120. Plus mass of B, velocity of B. Yes, it's a positive, so I don't have to do, mass of B is this one. And the velocity of B is right there. Excellent. So as you can see, we have everything we need, and we are gonna just solve it for the initial velocity of object A, which will come up to be 0.790 meter frame it. So let's comment on this result. Remember, the magnitude of a velocity is the speed, right? Velocity is, however, a vector, so we need to give the direction and also the magnitude. In this case, as you can see, is a positive 0.790, means it goes toward the positive x-axis. Let's move on to part B, where it asks to calculate the change in the total kinetic energy the system undergoes during the collision. So the change in kinetic energy. What does it mean? Change of kinetic energy. Basically, is nothing else than delta K. You do recall that delta K, change in kinetic energy, you need to do kinetic energy final of the system minus the kinetic energy initial of the system. You also recall that the kinetic energy is 1/2 mv squared. This is a quick recall. Considering that we have two bodies, right? We have to compute as follow. Kinetic energy initial will be the kinetic energy initial of body A plus the kinetic energy of body B, initial. Kinetic energy final will be, again, body A, but with the final velocity of body A. And here again, body B, final velocity of body B. Okay, so that's all we need to compute. Now remember, the initial velocity of body B was 0 because at rest. So basically it's very simple. In this case it will be 1/2 mass of body A and how fast is going. Final result in joule. Here is going to be 1/2 so this is a final, the one we computed. This is the mass of B. Don't forget to square, and this comes out to be at 0.0757 joule. All right? So please refer to the above to plug in all these very important numbers. This is the mass of B, mass of A, final velocity of A, and final velocity of B. Am I done? No, because I'm going to do the change, delta K. So K final of those two bodies minus K initial. So let's do that. The K final minus initial. So as you can see, you will obtain a negative. Why negative? Because there is a decrease. So a decrease of the total kinetic energy during the collision. So it is indeed decreasing, arrow down always mean decreasing. So while the momentum is conserved, the energy is not. There is a loss. A block of mass 1 kilogram and a block of 3 kilo are forced together by a spring. The system, so they are pushed together. The system is released from rest. The friction is down to 0, is a frictionless surface, and the mass of the spring is also negligible. Block B acquire a speed of 120. So let me show you. Perhaps when it's released, the spring stretch, and block B acquire a speed of 120 meters per second. What is the final velocity of block A? So block A is here. What is this final velocity of block A? This one I know is the final velocity of block B, but what is for A? So that's what we want to find in part A of this problem. In part B, we are going to find how much potential energy, so the potential energy stored in the spring, so it's the potential energy of the spring, what I call it the U of the spring. Let's compute that too. So I'm going to add a little bit more theory in this great problem. All right, so we know that they are all at rest at the very beginning. I know there is a momentum. I know that the momentum is conserved. Conservation of momentum. I'm gonna implement my knowledge. Okay, so here is all initial for the body, and here I'm gonna put equal to the final stage of the system. I'm gonna do it theoretically, mass A, velocity of A initially, plus mass of B, velocity of B initially, equal the final mass of A, velocity of A final, plus mass of B, velocity of B final. This is a classic treatment. I know this is a 0, this is a 0. Why? Because they are at rest. So I'm left with this equation, 0 equal final plus the momentum of B final. Okay, great. What do I know? Take a look to V of B. If this is the positive x-axis, V of B is indeed positive, right? This is going to be positive. But how about the final velocity of object A? Positive or negative? Negative, because it's opposite to the direction of the x-axis. So this one has to be negative. So this is a very simple equation that I'm going to solve it. 0 equal negative, mass of A was 1 kilo, velocity, that's one I want to find, mass of B was 3, and velocity final of B was 120. So if you solved for V of A final, you obtain a value that is 360 meter per second. This is the magnitude of A. How about the direction? Well, as you see above, right here, is to the left. All right, very good. How about part B, which we want to find the potential energy U of the spring. Remember, we have a spring which is quantified by K, the spring constant. All the time you have a spring, I want you to think about the Hooke's law, right there. And that the potential energy of a spring is really called elastic potential. So it's what we called in the past capital U-E-L, abbreviation for elastic. Now, we know that initially the spring is fully compressed. So basically this initial elastic potential energy is really gonna be stored at the maximum. When is unleashed, when is stretched, the potential energy final elastic will be 0 because it unleashed. So here is a compressed, and here the spring really doesn't have any more potential. It reaches its maximum stretching, its maximum elongation. So we need only to reason on this initial potential energy elastic. Let me write it down like this one, capital U elastic, initial. You remember that when there is a potential energy, there is also a kinetic energy, a change in kinetic energy. and because there is a work, right, the work theorem. So in this case, this potential energy is equal to the change in kinetic energy. So I'm gonna do equal delta K, which means kinetic energy final minus kinetic energy initial. Unfortunately, or good for us, you remember those two objects initially are at rest, right? So the initial velocity is 0 because a kinetic energy, remember, depends on how fast is moving. So immediately, because of this condition, I'm gonna say goodbye to kinetic energy initially being 0. So the equation I wanna solve is that my potential energy elastic initially will be equal to the kinetic energy final of both objects. And it does make sense, right? This object, these two blocks, here is initially, and this is the final. So the kinetic energy of the system depends on this final velocity, which we computed already. So we are in good shape. All right, let's do this one. It will be 1/2 the mass of A, velocity of A final, plus 1/2 the mass of B, velocity of B final. Oh, you wonder what is the kinetic energy initial? Kinetic energy will be the same, but it will be, instead of a final, you will put an I. Okay? But I know that this initial energy is 0 at rest. So basically, I just plug in straightforward what I know. The mass, how fast is moving body A, which we found it. Mass of B, 3 kilo. And how fast is moving to the right, 120 meter. Remember that the kilogram is in joule. This gives rise to the joule as a unit of measurement. And the final answer is that the energy elastic potential stored in the spring comes out to be 864 joule. Frame it. All right. In this problem, we are on a frictionless air track. You have a glider of a mass given to you, which is moving to the right. So this is a positive if we assume the positive x-axis pointing this way. And it collides with a stationary, you see stationary means at rest, so this velocity will be 0 of this object which has that mass. We want to find in part A the momentum of these two glider systems, so P, the momentum of a system. When, wait a second, before the collision. All right, let's focus on part A. I know I'm going to call mass of A. I know mass of B. And I know that the momentum P is given by mv, right? Vector and vector, because the momentum is a vector like the velocity. So the P momentum P before the collision, I'm going to call it B net before. So this means that the P net will be given by momentum initial of object A plus the momentum initially of object B. Yes, if I want to be nice, I'm gonna put the x-axis right there that I put up there in yellow, just to let you know I'm computing the momentum net before the collision along the x-axis. Let's spell it out. Momentum of A, this is initially, and this is the momentum of B initially. All right? Let's not forget that this is B is at rest. So this term goes down to 0. So we are left only with the momentum of A, velocity of A initially. So super simple. Right? Because this is A and this is mass A. So final answer right. Let's do part B. In part B, we want to find the net momentum. Look, net momentum after the collision. Okay, so I'm going to say P net after is my big question mark. Now, after the collision, there is a momentum, and the momentum is conserved. Means the initial momentum along the x-axis is going to be equal to the final momentum along the x-axis. So basically it's almost given the answer, because it will be exactly this value. Just a quick consideration. Remember, object A is moving at 120, right, meter per second. So this quantity initially will be 0.150 kilo, its mass, multiply 120. So again, will come out 0.180 kilo meter per second square. So, excuse me, meter per second. So this is equal also your final after the collision. In part C, it says use answer A and B to find the speed of the glider after the collision. So speed after collision. So we have an interesting problem here, because when they collide, these two glider, they stick together. It says right here. So imagine the situation. Okay? Imagine. This is a B that is stationary at rest. Here is A moving toward. This is before. Just right after. So right after B, when it's stationary and the A slam into it, they form one body, right? This is one body, a blue body. It moves away with a certain speed, which we want to compute, right? After they stick together, how fast are they moving away? So what do we have here? We have object A, which has a mass. Object B, which has a mass. I know that in this case, P initial equal momentum final. We computed before. Why? Because B is at rest and the value is the very famous kilometer per second. Here, in this situation, you have one object that has a mass A, then I have to add the mass B. So this is going to be a combined mass, but the one I want to find is V. So these two values has to be equal, right? P initial has to be equal to the final stage. Equal. Okay? This will be the final between the two, but now is a situation before and then is after the collision, so they have to be equal. What does it mean? Here in mathematical term, written a little bit better, equal mass of A plus mass of B multiply V, that is the one I want to solve. So as you can see, my V comes out from this equation. And the mass of the two bodies was and if you do the math, you will obtain at 0.450 meter per second frame it. So we know how fast is this sticking together object moving to the right. I think there is also another part D. We want to find the kinetic energy conserved during the collision. Okay, so kinetic energy. In part D, we want to find the kinetic energy, what we call just K. So, kinetic energy of object A will be 1/2 mVA initially square. Kinetic energy of body B initially will be mVB initially square, but this is the one at rest, so V equals 0, no kinetic energy. So this is the initial. Now I'm going to reason on the final stage, what would be the kinetic energy final? Because it's asking me for both stages, right? Before the collision and then after. Final is when we have the two bodies combined, the mass combined. So this kinetic energy will be 1/2 the combined mass, MA plus MB, multiplied how fast is moving. So now I just have to plug in all the data to compute everything. For this one, I'm gonna here. Mass of object A. How fast was moving A. Final answer. Joule. And here I have to compute it because I have to add those mass. So I have to do plus and the new V that I just found, so for this one, the final answer will come out to be 0.040 joule, this one too. So look at these two numbers. This is a 0.1. This is a 0.0. My question to you is, the kinetic energy is conserved? If it was, it would be the same value. Since it is not 0.1 and 0.04, the answer is that no. Why is not conserved? Because the two objects stick together. Because they stick together.
Energy. Physics. Hyperbeam galaxies. Planetary nebula. Supernova explosions. Energy. From light years away. Physics.